Today, we will be discussing about design patterns in LabVIEW. Before I begin the session, I'd like to have a small poll. Have you heard about the design patterns in programming? Okay, it looks like approximately half of the attendees have prior knowledge about design patterns in programming in general, and the other half don't. So let's go through the basics of design patterns in general. What are design patterns? Design patterns are general solutions to commonly occurring problems. In this session, however, we confine their usage to programming solutions. Design patterns are not finished solutions, but rather they offer a framework which a developer can work on. Now, why do we need this framework? Will it help us in our everyday programming solutions? What are the advantages of using design patterns in programming? The first and major advantage of using design patterns is that they are reusable. Inherently, they can be reused in multiple situations. However, this is not the same as code reuse. Code reuse is when you use pre-existing code to solve a similar problem. A design pattern, however, does not deal with specifics. So, a design pattern is like a weapon that can be used to attack a diverse range of applications. Just as the template in the background can be used to create different presentations. Design patterns don't emerge until they are tried and tested rigorously for years by the industry experts. They are widely accepted general solutions that help a variety of developers. Just as the design, prototype, deploy mantra, which is used widely by the industry to develop products and solutions, design patterns also emerge after rigorous testing. Due to large community of developers that use common design patterns, a lot of help and support resources are also accessible to new developers. So anyone who is going to use a design pattern can expect a lot of resources available online to help them. Design patterns are known widely amongst developers. They are most commonly used. Hence, the code created using design patterns can be understood with extreme ease. A developer who used a design pattern to program for whatever solution, he has automatically provided tons and tons of documentation on the basic working of the code. Now that we have understood what defines a design pattern, let's see what features are exhibited by a good design pattern. A good design pattern can be modified to a great extent to suit the necessity at hand. Since design patterns are general, it is very important that it is accommodating to changes. Now, there also has to be room for scaling a particular pattern to add new features and to increase it quantitatively. For example, a pattern that can be used to process one vibration signal should be extendable to any number of them. A pattern should also stand the test of time. Future developers should be able to understand and troubleshoot possible issues easily. In other words, the design pattern has to be flexible, extendable to add new features, and maintainable through years to come. Now, I can go ahead and explain a few design patterns, naming them. Instead of that, a bottom-up approach starting with an application in mind would help us understand design patterns better. Suppose there are two tasks, 1 and 2. These tasks work at different rates and consume different CPU resources. Task 2 works on command sent by task 1. This is a very general situation which you might encounter every day. And a specific example of this could be one where task 1 detects the pressure level of a chamber and task 2 implements an alarm response. Task 1 has to communicate to task 2 that an alarm is triggered when the pressure level increases a certain value. Now, how do we implement this kind of an architecture in a programming language or in LabVIEW? Now let's go to LabVIEW and see how we can implement this. Here's a single loop, a single while loop in which there are 3 tasks. For simplicity, I've used loop timers to create delay in these tasks. The first task is just the user interface. As you can see, there are 3 controls in it, a tank, an OK, and a numeric indicator. The second task is just an empty frame. By the empty frame, what I mean is there is very little or no processing happening in this frame. The third task has a wait in a frame of 2 seconds. By keeping a simulated delay of wait, I mean to say that this loop or this process takes a lot more time than tasks 1 or 2. As we observed, the second task is extremely fast, probably an arithmetic equation. The third task is reasonably slow, and it might be a fast Fourier transform, any spectral analysis, or probably data logging to a file. Now, these tasks need not run at the same rate. So I've kept 3 tasks on the LabVIEW VI. Now take these as to be the 3 tasks. Task 1 commands task 2 and 3 to run. Now as you observe, all 3 of them are in the same while loop, and hence they inherently share the same timing. So if there are 3 tasks in the same loop, the slowest one determines the timing execution of the entire loop. In this case, the slowest one is task 3, which takes 2 seconds to complete. And hence, as you see, the entire loop takes 2 seconds to iterate. Now this is not desirable behavior because the second task is considerably faster than the first task, and we would expect the second task to complete in tandem with the user interface. Now let's see how this works. I run this VI and then I increase the control of the tank control. As you see, tank 1 increases with a little delay and the task 2's tank increases with a little more delay. However, since task 2 has no delay in it, we would expect the task 2's delay to be non-existent. We would expect immediate response. However, that is not the case. And that is because task 3's delay is 2 seconds and that creeps into the other 2 tasks. Now, how do we overcome this? We overcome this by using the master-slave design pattern. What we do here is we break the single loop into 3 different loops, one of which we assign to be the master and the other 2 to be slaves. The VI, which does the master-slave design pattern, will look like this. This contains the same 3 tasks. I've just broken down 3 tasks into 3 different loops. The first loop contains the first task, which is the user interface. The second loop contains the second task, which is almost 0 delay. The third task is the heavy one, which has 1.5 seconds of delay. Now, I've used local variables for the tank control to communicate between the three loops. So the moment I change the value of the tank control, that value is immediately reflected in the local variables in the other two loops, that is the slave loops. Now let's see what happens when I run this VI. I increase the tank control, and as you see, the second task's indicator, tank indicator, increases instantaneously. There is absolutely no delay in it. However, the third task, the other slave task, increases or decreases with a certain delay, which is expected. Hence, by using master-slave design pattern, which essentially means by separating the three tasks into three different loops, we are eliminating the delay, or we are eliminating the delay that creeps into the other slave task by the slave task which has a lot of delay. Now, let's check if this is the desirable way to implement a master-slave design pattern. This is what is happening now, contrary to the previous. There is one master, one slave, and two slaves. The master and the first slave are running pretty fast. The second slave, however, is slow as expected. Now, neither master nor the fastest slave loop is being affected by the delay in the slower loop. However, there is an inherent disadvantage to this architecture. Local variables are considerably slower. They need to continuously poll to check if the control's value has changed. There is a better implementation of this using notifiers. Notifiers are a tool to synchronize different processes working at different rates. Now this is the notifier implementation of the same VI using master-slave design pattern. As you can see, I have used 4 different notifier VIs here. You can find the notifier palette under programming in synchronization under notifier operations. Here you will see the different notifier VIs. The first VI that I use is the obtain notifier. Notifier, as I told you, is a tool to synchronize different processes. It is a memory location in the LabVIEW memory which holds a single value at a time. This can be used as a transporter of data across different loops. For example, in this loop, I have a send notification VI. The send notification VI sends a message to all the receiver notification VIs, which is the waiter notification. So in this instance, what I'm doing is I'm using the tank control and I'm sending the tank control value using the send notification. Now what happens in the slave loops? In the 2 slave loops, I have 2 waiter notification VIs which are ready to receive the values that are sent using send notification. The advantage is that the wait on notification VI does not execute until the send notification VI has received some message. Now, for example, let us run this VI. Now I increase the time control and press the OK button, and immediately the message is being sent. As you can see, there is absolutely no delay in the second slave task, and there is expected 1.5 seconds of delay in the third task. This is the master slave design pattern and is most often used when there is a user interface that needs to be polled continuously. As you can see, this architecture consumes far lesser resources than using local variables. To understand that better, we can check on the task manager during the execution of both of these VIs. Now, I'm running the VI with the local variables. Let's check on task manager and how much CPU usage. As you can see, the CPU usage is 63%, and I'm using no user interface at all. In the idle time, it is consuming 6% of the CPU. Now let me stop this VI and use the master-slave architecture with notifiers. Here, when I run this, the CPU usage consumed is significantly lesser. It is at 38 to 40%, which is a reasonable decrease in CPU usage. Now, let's look at a different application. Suppose we have two tasks again. Task 1 continuously generates data and task 2 continuously receives and processes it. Let's look at this in new light and not through the master-slave perspective. For lossless data transfer, observe that the tasks have to generate and analyze data at exactly the same rate. Now let's look at a simple implementation of this in LabVIEW. I placed two tasks in a single while loop, task 1 and task 2. The first task is just UI operation. There is a random number generator and the send button simply sends a value to task 2. Task 2, however, is a heavy process. It takes 1.5 seconds to execute. Now, when I run this VI, what I would expect is immediate reflection on the waveform chart of the data that I send through the random number generator. However, what I observe is different. When I click on send around 10 times, the waveform chart is updating very slowly. It updates at a rate of 1.5 seconds, which is expected, but is definitely not desirable. Now, what do we do to avoid this situation? We have a task which sends data continuously and a task which analyzes it. But however, they both don't run at the same rate. Now, how do we tackle this situation? This situation is pretty commonplace, and a very good example of this is the tasks of acquiring data and analyzing using fast Fourier transform. The acquisition is clock based, which means it generates data at a constant rate. However, the analysis is done in software, which is an operation that is scheduled by the OS. So if the analysis code slows down, we will definitely miss samples. So we have a generation code that generates data continuously, and we have a processing code that is determined by various OS parameters, which is non-deterministic. Now, how do we tackle this kind of situation? What we use here is again similar to the master-slave architecture. Suppose, for example, we just extrapolate the master-slave architecture to this. What will happen? Now, as we observed, the notifier holds exactly one sample at a time. It holds exactly one value of data. Now, if I run this VI and I change the tank control, as you can see, the task 2 is not able to keep up with the tank control. I'm sending exactly one value at a time, and the last task is able to receive one sample in every 1.5 seconds. So the data which I'm sending in between is being lost. So the master-slave architecture is incapable of handling the situation without loss of data. So what we do here is a different architecture. We use a buffer. We use a queue. A buffer separates the generator from the analyzer. This is implemented as a queue in the LabVIEW VI. Now let's see the implementation of queues in LabVIEW. Queues in LabVIEW look very similar in implementation with notifiers. As you can see, the queue API is also located in the programming palette under queue operations. Queue is very similar to notifier apart from a major difference, which is that queue can buffer data. It can hold multiple samples of data up to a certain limit. Now, let's observe what is going on in the block diagram of this VI. There is a producer, there is a consumer. These are basically the two tasks that we spoke about in the last single loop VI. The producer is simply generating random number of data. The consumer is analyzing this data, which is simulated using a delay function of 1 second. However, they are both not located in the same while loop. They are running parallelly and simultaneously, and the data is being communicated through them using queues. Now let's see what happens when I run this VI. I run this VI and I click on send. As you see, there is data on the waveform chart. This is very expected. Now let's see what happens if I continuously keep pressing send around 10 times. I've pressed the send button 10 times and left it. Now you can see the data is still being plotted on the waveform chart, although I have stopped hitting on the send button. This is because the queue is buffering the data and is saving it for further use by the consumer loop. This architecture inherently avoids loss of data and is a resolution to the problem where the consumer loop is significantly slower than the producer loop. Now, one more simple question on notifiers to emphasize the difference between notifiers and queues. Do notifiers buffer data? As in, can notifiers hold more than one sample of data? There seems to be a small confusion amongst the attendees. Around 80% of them have voted no, which is a good response. However, I think it's a good time to emphasize the difference between queues and notifiers. Queues and notifiers are both synchronization techniques to help communicate data between different loops. However, one major difference between them is that queues can hold multiple samples of data. They can buffer data. They can queue data within themselves and dequeue it whenever necessary. However, notifiers are like alarm responses. They hold single values of data and hold that value until a new value is written or overwritten into it.